Hello, good morning, good afternoon. My name is David Bosso, professor at Skoltech. Today I'm going to talk to you about the basic math and the basic modeling for power systems. I will try to introduce you very basic concepts on the math used for understanding power systems and the math used to build something more complex. I will also try to bring you connection from the DC circuits or the circuit that you know from the higher school to the way we are solving AC circuits of circuits from power systems. I'm going to introduce you what are the conceptual things. Well, first I will talk about circuit phase, single phase circuits, balance, three-phase circuits, electrical transmission lines, and per unit analysis, which is very important. Let's start with circuits. So, well, everyone knows that we are using AC in our power system. Most of the things are working with AC, and the transmission grid actually is delivering energy in AC, or alternating current. And this basically was the idea of Tesla at the very beginning. But at the very beginning, the conception of the electricity, DC or direct current, was the first standard. So Thomas Edison actually was fighting to implement systems that can deliver energy in DC. So basically very small microgrids on DC. Still, we have plenty of things that they are working in DC, like our computers, our cell phone, everything that have some battery actually is working DC. So, well, you probably know about, even if you're not electrical engineering, you know about equation in DC, like Ohm's law or some balance equation. But the thing is like, we are here to understand better how works AC systems. So let's start with a very basic definition. What is a sinusoidal wave? We are going to use that for a while. So let's imagine that you have a sinusoidal wave, and we want to model. So that the typical thing is like, we can model like this equation. We are using cosine, but actually can represent any sinusoidal wave or cosine. Basically, this function is a function that depends on t, v, and it's represented by this maximum or the amplitude, maximum value can take of the amplitude. Omega is representing what is called angular frequency, and t is the time component, and phi, the last term, is representing shifting with regard to times equal to 0. So some very basic definition is like, we call period t, and also is measured in seconds, to the time that you are completing one cycle. And the number of cycles that you have per second is called frequency, and it is not measuring 1/seconds, basically it's measuring Earth. Angular frequency is this time 2 pi divided by t, or 2 times the frequency is measured in radians per seconds, and this is the element that we have in here. What is called phase angle, or phi, representing this shifting. Okay, this one is a very basic definition, right? What you have here, and we are going to start with the how we can simplify this thing, because I have not go into details how the electricity is generated. We are not going to detail, but you can imagine that generators are generating this kind of signal. It's a sinusoidal signal, and this is the kind of signal which is transmitted through lines. And this is the signal that we have in our sockets, where we are connecting our refrigerator or anything else. So one important thing here is like, when phi is positive, means like sinusoidal wave is shifted to the left. So you can think about that. So this is why phi is positive. And very important metric that we are going to use here, very important value, is what is called RMS or root of means of the square. And how we can compute this root mean square value for this sinusoidal wave. So basically we take the integral for over one period, right, from some reference t0 up to t0 plus t, like when we complete one period. And yes, we have this, this is basically this bt dt signal to the square, of course. So we integrate the square of this value and then we make the square root. Of course, we normalize. So the important things here is like, well, this root means a square. It is just a single value. It doesn't change along the time. And we will use this in the future. This will be a very important value. And you can see, well, you have a very special relationship between the amplitude of the wave and these values. Is something a little bit in here, like not, it's BRM divided by 1.14, the square root of 2. Okay, what is a phasor? We will come out with a very interesting tool that engineers are using, and this is called phasors. So let's imagine we have this signal, this V, which is in time domain. So we have this sinusoidal signal in time domain, which represent, for example, the voltage that you have in some specific point. Then, well, there is we can actually transform this omega, this angular frequency, so it's constant, like for example, like 50 Hz or 60 Hz. So what it's important here is just to, well, this amplitude and this phase angle. So we can actually represent the same information with something which is called phasor. And the phasor is basically this representation of this time domain function in a complex domain. So we have in complex domain, we can represent like some module and some angle. This is the case where we have this phasor polar form, but also we can represent like a rectangular form. So you are probably very familiar with complex numbers, and you should be very familiar with complex numbers. So you have the possibility to go from these sines and cosines to this polar representation using this Euler identity. And well, you have some kind of nice interpretation of this sinusoidal wave I have here on the top, that yes, you can understand this sinusoidal wave like a vector which is rotating. Okay, but there are something much more interesting. It is the properties of these phasors. This phasor basically is a complex number, so we are representing like a complex number. We also know that like a frequency domain, so we represent the same information in a different domain. And these have very nice properties. So if you sum up several sinusoidal waves, you can sum up sines and cosines, and then you arrange all these terms, and then you come up with something else. So this is the same if you are summing up phasors, right? Why this is very nice? Because it's much more easy to sum complex number than cosines and sines, right? And this is something that we are going to exploit. We are going to use pretty much in the way we are modeling the physical equation of the power systems in AC, right? So probably you remember what is the Kirchhoff laws. If not, so I will remind you. So let's imagine that you have any kind of circuit. This circuit basically is a voltage source, whatever is in DC or in AC. Then you have some resistance here. So you have several resistance. So Kirchhoff law basically tells you what are relationship between voltages and relationship between currents. So there are two Kirchhoff laws. So the first one is the voltage law, and the second one is the current law. What says the voltage law? Well, the voltage law says like, well, if you take a loop in this circuit, like for example this loop, or I'm taking the other loop, I can take this outer loop also. Yeah. So if I take in any of these loops, let me delete one. So the sum of all voltage drops at every part. So I have a voltage drop in here in this generator. So it means like, well, we are increasing the voltage, and there is a voltage drop in this resistance. Then I have this voltage drop in this other resistance, and then there is another voltage drop in this resistance. So the sum of all these voltage drops, some of them positive or negative, if you are passive, if this is a passive element or it's a generator, it will be always zero. And if we have a source of generation which is following a sinusoidal wave, we have these changes over the time, right? So resistance are also observing the sinusoidal wave. The nice thing is like, well, we can transform that in complex numbers, and actually it's working the same. So this is very nice because we are using phasors, those B's and this bold B that we are using, and these help us to reduce the way that we are going to, and this help us to simplify the math that can govern this part. Well, the other Kirchhoff law is what is called Kirchhoff current law, and basically this is a balance equation. So you just pick up some node. For example, I will take this node, and then I see in this node, well, I have incoming here to this node, I have this current I4, I2, and I5. So basically I'm saying like whatever is in is also going out. So that's anything disappears, nothing disappears. So in other words, so I can say like, well, the summation of all currents in phasor form of these complex numbers is equal to 0. So of course, so we understand like in reality we have something like this. So we understand like in reality we have something like this, right? So we have these the real numbers or time domain numbers. So what we are representing with phasor is a kind of mathematical trick that help us to read out of this very complex summation of sines and cosine. Okay, remember, so we have these two important laws that they are governing most of the physics laws that happens in the circuits. So these two are important. So, but we have different elements. We have not only resistance or resistors, right? We have other kind of elements. We are classifying those elements depends on the behavior that they have, like in resistors, inductors, or capacitors. So a resistor basically is your kettle or your radiator, electrical radiator. An inductor is basically any kind of these spinning spirals that you have, for example, like speakers usually have that, like old ones. And capacitors, well, you see here some of them. So each of those elements, if they are purely resistive, purely inductive, or purely capacitive, they will behave in a different way in time. So let's imagine that we have a resistors here, right? We have this resistor, and well, forget about for a while for this L, which is the inductor. So we close this switcher, and then what is going to happen is like, well, the voltage that we are going to observe at the resistor actually following the same sinusoidal wave like the voltage that we have here in our source, right? So that's well, we are assuming like we are working with some sinusoidal wave, right? This is voltage of the source that depends on T. So we are going to observe something very similar here, but well, this is scale with the Ohm's law. The thing is like not all the elements are the same, and they have well, engineers actually have classified them in three main type of elements. So inductors of these spirals that I saw you before, actually they have a kind of very interesting behavior. Current and voltage also change from the moment that we close the switcher. So there is a transient period, and then there is a steady state value. So that is very typical when we have dynamical systems. What you see here is not necessarily what is happening in this circuit, but this is for anything which is have some dynamics. So you can observe some transient state and then some steady state, or transient period and then a steady state period. So it could be like this, or it could be something like this, and then it's reaching in another moment a steady state. So we are going to work during all this course only in a steady state. So we forget about these transients, and in power system, basically those transients are happening pretty fast. So it depends on which kind of systems you have. Like for example, gas networks have different times constant for the system itself. So transients happen even slower or maybe faster. So in this case, at electrical grids happen pretty fast, and we forget about that. So you will have other courses that can help you to understand better what's happened with those transients. Okay, let's start with the understanding of these different class of elements. Let's start with the one we call resistor, which is basically a resistance. I can tell you, like, well, in time domain, this the relationship between the voltage and the current basically is it's a linear relationship which is connected with this value R, which is the typical resistance of this element. This is mainly the Ohm's law, but for time domain, which is changing along the time. This time domain can be transformed into the complex domain or frequency domain through using those phasors that I just mentioned to you. And we see, like, well, if we see those phasors as vectors, we see those two vectors are aligned. So we are saying for resistive elements or resistors, the current and the voltage are in phase. Okay, well, we have the other two kind of elements. We have this inductor, and this capacitor. Inductor and capacitor also have a very special relationship between current and voltage, current I and voltage V, and this can be represented in the frequency domain or this phasor form, and this is basically the way that we represent them. I'm not going into detail of that because, of course, so you see, like, this is a kind of dynamic equation which depends on t with the derivative of t, and that actually have some transient values. It's the way that we are going to use. So if we represent those vectors like the v and I, like a complex number in the complex plane, so we see, like, the current is lagging the voltage, or we can say also the voltage is leading the current. And this is something which is very typical for electrical engineers, so they are very used to say that. Something similar we have for the capacitors. So in the capacitor we will have just a linear relationship between current and voltage in phasor or in frequency domain. In this case, like, the current will be leading the voltage, right? So this is voltage, this is current. So we can actually create some elements like we call Z, or also impedance, that will compile any kind of composition of resistor, inductor, or capacitor. So let's if we have a composition of a resistor plus a capacitor plus an inductor, So basically we can make this into a box, or we can put this as equivalent. This is what is called impedance, and that will have some equivalence between these R, L, sorry, this is C and L. This is transform plus like this GI. So those elements, like this part is for the complex part of this impedance, and this R is the real parts of the impedance. This complex part of the impedance is called reactance, and this reactance have to be with those capacitive elements and these inductive elements. Let's see a graphical example. We have one resistor, we have one capacitor, and we have one inductance in blue, orange, and green. Then we want to understand what is the voltage drop overall. So we know, like, well, this is from here to here, just this is the side. We have this voltage drop. We have this voltage drop for the next one is for the capacitor, and then for the line. So we want to understand how it looks like that. So the first thing that we can do, like that, this is graphical example, so we have not any values. Of course, if we have numbers, so we have to use complex numbers that I mentioned before. So let's remind that, well, whatever is the I, so let's put I in this 0 degrees, so in this axis, x-axis, and then to start to write how it looks like each of these elements. So for example, if we have, well, I have this side like this one. Let me go again. The side of this voltage drop in the resistance of this resistive element. I know that resistance are in phase with the current, so the elements, the resistant element is in phase with the current, so it means like whatever is the current will be the same for all of these three elements because they are in series. So whatever is the current, so the voltage will be also in this direction. So remember, we have this in orange we have this capacitor, so whatever is the value of the capacity, the capacity voltage always is, well, so let me start with the green one. So remember, this voltage is leading the current, so I will have whatever is this BL, and then finally I will have some drop from this point, right, for this BC, and the summation of these three vectors, this one, and this one, will be the final one, right? So this is BRCL. Okay. Well, this is more or less what you have in here. Okay, we can actually generalize that, right? Let's imagine that you have we have here a source, right? So we have a source of voltage I call V between A and B, and then connected to this source I have 1, 2 up to n elements, and there is just one current going through this circuit, so it will be the same. Remember, this bold I is representing a phasor, and this is basically a sinusoidal wave. So I will have the equivalent of this bold I, this one, in the time domain. So I know, like, because everything this is in series, this current must be the same. So how I can actually extend, well, and C1 is any general elements, any impedance elements. So remember that if you have resistance, so you can remember very well. So the voltage drop in between A and B, it will be the same of the summation of the voltage drop between A at C1. This is the voltage drop at C2, so on and so forth, and the voltage drop at Cn. So this is, if you remember, this is the Kirchhoff voltage law. Okay, and then we can combine all of them, so we have kind of C equivalent when we have series elements. So we have the voltage between A and B is equal to some C equivalent multiplied by I. So if you remember when you have this kind of circuit in the high school, so you were using resistance, and it was basically the same. So if you have something in series, the equivalence will be the summation of all the resistance. So we can think about something similar when we have parallel connection. Let's imagine we have here, again, we have a source of voltage, and then we have a current just going outside from this voltage, and this current is split into different branches from 1 up to n branch. So every branch actually will have different current because actually it's split. Each of these current actually is representing a sinusoidal wave. And the current splitting will depend on the values of C1, C2, and Cn, so on and so forth. So if you have from your higher school something which is a resistance like this, yeah, and this is in DC, let's say it's 5 volts. So you remember how to split this in two or more. And the idea is like, like what is the voltage between this point and this point, let's say A and B, is equal to this between A and B, and this is also equal between A and B, right? Because we don't have any resistance, we have no elements in between these 2 points. So all of them, the voltage between all of them is the same. So we can write this equivalence like this. Well, the voltage between A and B is basically this volt V, and the current in 1, right? This current in 1, current I1, will be V divided by C1, right? And then I know, like, well, by Kirchhoff current law, like the summation of all the current have to be equal to the initial current. So this initial current here, right? Okay, so we end up with this expression, and then we, of course, if we move things around, we can actually have some equivalence of the C in terms of this one. So basically, this is how we can apply Kirchhoff voltage law and Kirchhoff current law. Remember, like I call impedance to this element, which is a very general element, can have just a pure resistance, or it can have also elements of capacitors or inductors, and this is why we call reactance. Okay, what is the unit for measuring impedance? Is ohms. And then we have, and this is important remark here, like this C is a complex number. Okay, another important element that we are going to use is called admittance. And admittance basically is the inverse of this impedance. It's not the inverse of the resistance, it is not the inverse of the reactance, it's the inverse of a complex number, which is the impedance. And the inverse of a complex number is also another complex number. So we get here J and B. And J is the real part of this complex number, it's called conductance, and B is the susceptance, and this is measured in Siemens. Let's start to summarize what we see up to now. So remember from the high school that you really understood how are the physics laws of the circuits in DC. If you have a resistive element, you have current and you have voltage, current and voltage doesn't change over the time. So remember that you knew that what is the Ohm's law, and also you knew like the power is voltage time I, because I and V, like current and voltage, doesn't change along the time. So the power is always constant. Whatever is the voltage or whatever is the I, so the power that this source is leaving to this resistance, is delivering to this resistance, is always constant over the time. This is not the case in AC. So what we see in AC is like, well, now we have sources of voltage that depends on T, so the current also depends on T. And we have elements which are a little bit more complex, this C, and this C actually is the equivalent of this resistance, but it can have other elements. So we already seen like, well, the voltage on T actually is, well, this, resistive part that is changing over the time, I is changing over the time, but we have other elements that is connected. And of course, so we haven't seen that, but you can imagine, like, well, if you have at any point, you have you can measure current and you can measure voltage. At every moment, you can know what is the power which is delivered in this point, right? So if we are considering this C, so we have what are the power that we are delivering for this C. So whatever is the elements L, so how much capacity for inductive elements we have in C, so we may have some shifting to the left, to the right of the voltage with regard to the current. And what is the power? Basically, the power is like, well, if in second number 6, so I have multiplication of this thing times this thing, like this current time voltage, so this will give me the power. So we have seen like this function of the voltage over the time actually can be represented in a very, very, very simple way that looks like the Ohm's law. That is the same case for the powers, how looks like the power. So this is what we are going to see in the next part.